Let's move on to sorting algorithms. In a search algorithm, you have some kind of list and you're just checking out each element. However, in a sorting algorithm, you're changing the order of elements in an array. Let's say you wanted to sort these guys by height. You have some decisions to make first. Should I put the shortest element on this end or on this end? And what algorithm should I use to sort? You could just compare every element to every other element until you have everything in order. This is called the naive approach, since there's no real trick or cool algorithm involved there. The naive approach is normally the first thing your mind skips to when you see a new problem. It makes you think, I know I could do it this way and everything's going to be right, but there's probably a smarter way to do this. Sorting is kind of a weird topic. You'll rarely be given a problem that can't be solved with one of the classic sorting algorithms we go through here. As far as interviews are concerned, it's important to understand how sorting algorithms work and have their runtimes memorized so you can answer complexity problems really fast. Lastly, you should make sure you've considered whether your sorting algorithm is in place or not. An in-place sorting algorithm just rearranges the elements in the data structure they're already in without needing to copy everything to a new data structure. These algorithms have low space complexity because you don't need to recreate the data structure. Often you'll have that classic trade-off when you use less space or use less time. It doesn't really matter for arrays with 10 numbers, but if you have millions or billions of data points, it makes a huge difference. It'll never hurt to mention that in an interview. You can pick one way over the other, but say while you're doing so. The more reasons you can provide for your choices, the smarter you seem. Bubble sort, or sinking sort, is a naive approach, like I described before. You'll go through your array comparing elements side by side and switching them whenever necessary. Let me illustrate with a quick example. We'll start at the beginning and we'll compare the first two elements. If the first element is bigger than the second one, we'll switch them. Great, we've made one switch, so now we can move on over to the next two elements. Looks like we need a switch here as well. Alright, now we can move along to the next two elements. And again, looks like our first element is bigger than our second one, so we'll need to switch. Okay, now we can compare the last two elements in the array. And once again, the first element is bigger than the second one, so we'll need to switch. Alright, now we're done with this round. Okay, now that we've passed through the array one time, we should count up the number of comparisons we needed. It took us 4 comparisons to get through 5 elements. I think it's safe to say that our runtime for this step was n-1, since the array size was 5. So, with our n-1 comparisons, what actually changed? The array's still not actually sorted, but it looks a little bit better now. The largest element, 8, moved up to the end of the array where it belongs. This is actually why this method is called bubble sort. In each iteration, the largest element in the array will bubble on up to the top. So by that logic, in the next iteration, the number 7 should bubble up to right below 8. Let's repeat the process. Again, we're going to start at the bottom and work our way up to the top. Looks like we need to switch on our first step. Let's move to step 2 now. It looks like we actually don't need to flip these two for the first time. This first element is actually less than that second element, so we have nothing to do. Awesome. We do need to flip 7 and 0 though, and the last two elements are in order, so no work here. Again, we had to do 4 steps, which is still n-1. Okay, now we're going to have to do 2 more rounds of this, but I don't want to bore you with the details. Let me show you what the next iteration of comparisons looks like. I did another iteration, but not much has changed. I just had to flip the 3 and the 0 to look like this. Again, the biggest element left, 3, bubbled up to the place it belongs, but we still have work to do. And again, note that this took 4 steps, so n-1 steps. We only have 1 iteration left. Let me show you what that looks like. This time we only had to flip the 0 and the 1, and we're done. Great, so what's the efficiency of this algorithm? Well, we had to go through pretty much the whole array a lot of times. Here's roughly what we did. Overall, we had to do 4 or n-1 iterations. And at each step, we did n-1 comparisons. So n-1 comparisons for n-1 iterations gives us something like this. We can use a little algebra to figure out what this simplifies to. And we get something that looks like this. Again, don't worry too much if you can't do the algebra. The -1 isn't changing much for us, so you could always just do n times n equals n squared. Thus, we really don't need this -2n plus 1 bit. We can get rid of it, and that leaves us with this as the efficiency, big O of n squared. Actually, there's a way we could have saved ourselves some time with this algorithm. If you noticed, each time we went through the array, we compared the last few values, even though we really didn't need to after a while. It made sense to compare 7 and 8 when we were bubbling up 7, but when we were bubbling up some of the lower numbers, this comparison didn't really change anything. The most common version of bubble sort actually leaves out this step every time of comparing the last few when you really don't need to do that. It assumes that after the first iteration, you know that 8 is in the right place, so you don't need to check it against anything else later. Again, this will save us some time, but it's not going to change our overall runtime of big O of n squared. I have a couple quick notes for you. Okay, so we understand why the worst case and the average case are going to be big O of n squared. However, the best case is actually going to be big O of n. The best case would either be that the array was already sorted, in which we can just go through it once, see that it's sorted, and not have to do anything else. Or if there's only one number that needs to be bubbled up to a new place in the array. And one last thing. We didn't have to use anything extra to do our sort. We had no extra arrays, no extra data structures, nothing like that. Bubble sort is a great example of an in-place sorting algorithm. So the space complexity is constant, meaning we didn't need any extra arrays or data structures in the whole process. Let's talk about another popular sorting algorithm called merge sort. The overall idea is that you split a huge array down as much as possible and then over time build it back up, doing your comparisons and sorting at each step along the way. The general idea of breaking up an array, sorting all the parts of it, and then building it back up again is called divide and conquer. Several efficient sorting algorithms have this principle at their core. Okay, let's see how merge sort works with an example. First, we break up the array into a bunch of arrays with one element each. Now we need to start building it back up again. You may wonder why the one leftover element goes at the beginning and not the end. Don't worry too much about details like that. They'll differ depending on the implementation. However, this step should only have arrays of size 2 and size 1 left. First, we compare these two elements to see which one is smaller. Since 1 is smaller, it'll go first in our new array, and since 3 is bigger, it'll go second. Now we move on and do this with the next pair of arrays. Again, 7 is bigger than 0, so in our new array, we put 0 in the first spot and 7 in the second spot. And now we do this one last time, comparing the last two elements, 10 and 2, and putting them in order in a new array. Great, that was easy enough. Now, the last thing we want to do is keep track of the number of comparisons we did, so we can come back to it when we do our efficiency calculation. Overall, this step took 3 comparisons, each one in green. Okay, we're running out of space, so I'm going to clear everything off except this bottom row and move it on up. Now we're going to combine the first 2 arrays and the last 2 arrays and create an array of 3 and an array of 4. Now, these comparisons are a little more complicated. Here, we're comparing an array with 1 element to an array with 2 elements. We know that the array on the right is already sorted, so the first element of our new array is either going to come from here or the first element of this array. It looks like 1 is smaller, so that'll be our first element. Now we can move on to the next element in this array and compare it with this one. Since 3 is smaller than 8, we'll put 3 in this box. Now that we're done with this array, we can just take anything that's left in the other one and tack it on the end here. Great, let's move on to building this array. So we're going to start out comparing the first 2 elements of these arrays. That's 0 and 2. Since 0 is less than 2, 0 becomes the first element in our new array. Okay, so now we move on to the next element in this array, which is 7, and compare that to 2. 2 is less than 7, so we put 2 in the new array. We repeat again, checking 7 against 10, and fill them in at the end of the array accordingly. How many comparisons did we do in this step? Well, if you count up all the purple comparisons, that leaves us with 5. Okay, we're almost there. We just need to go through one more round to get our completely sorted array. This is going to start just like it did in the last round. We start off by comparing the first two elements of the two arrays that we have, so 1 and 0. Since 0 is smaller, it ends up going in this array, and we get rid of it in the old array. We move on, comparing 1 and 2, and end up with 1 being smaller, so 1 fills in the spot. We compare again with 2 and 3, and again with 3 and 7, and again with 8 and 7, and finally we're done. We have our newly sorted array. We need to keep track of the number of comparisons we did in this step, so I'll write 6 comparisons off to the side here. So how many overall comparisons was that? Well, let's try to find a pattern here. It looks like at each step we did one less comparison than the array we were building. So when we were building an array of 7, we only did 6 comparisons. When we were building an array of 3, we did 2 comparisons, an array of 2, 1 comparison, and an array of 4, we did 3 comparisons. I'm going to go ahead and call the length of each array m, just to make it a little easier for me. So if m is the size of the array that we're building, the number of comparisons is always going to be 1 less than that. It's going to be hard to get an exact number of comparisons here. However, we have a good friend that we can count on: approximation. Since we know that every iteration just cycles through the same 7 elements again and again, we know that the size of our arrays, or m, are always going to add up to 7 at the end. So again, here we have an array of 7, here we have an array of 4 and an array of 3, which adds up to 7, and here 1, 2, 2, and 2 adds up to 7. Since we're just doing divide and conquer, splitting up the array at each step, we can say that approximately we're going to do 7 comparisons at each step. Again, 7 is an upper bound. We're never going to do more than 7 comparisons, but at many steps we get close to 7. So to get the runtime of a sorting algorithm, you can normally multiply the number of overall iterations by the number of comparisons at each iteration. In bubble sort, we were doing n comparisons and n steps. We just proved that we're doing at most n comparisons at every step. But how many steps overall are we doing? Okay, so to sort an array of 7, we had to do 3 steps: 1, 2, and 3. Also, I should note some of the sub-processes that happened here. In order to sort this array of 2, we only had to do 1 step. When we were sorting an array of 3 or an array of 4, we needed to do 2 steps. We can use a nice table to keep track of all of that. Again, so when our array size was 7, we had to do 3 different steps. When our array was 3 or 4 numbers large, we had to do 2 steps. When our array was too large, we had to do 1 step, and if we just had 1 element, we don't need to do any comparisons, so no steps. I'm going to go ahead and fill in a few numbers here just for the sake of time. You can assume that I did these calculations on my own, and I encourage you to do them as well. Okay, so this might look a little bit familiar to you. Remember in binary search when we had a similar table, and the number of iterations incremented at every power of 2? Well, we actually have something pretty similar here. Instead of incrementing at the powers of 2, this time we're incrementing 1 after every power of 2. So in the binary search video, I proved why the number of iterations would be equal to log n. So if you need a refresher, you can go back there. Again, this time is a little different because it increments after the power of 2 instead of at the power of 2. Yet again, we're kind of relying on approximation here. We don't exactly care where the change happens as long as we capture the interval at which the change is happening. So in summary, we're doing roughly n comparisons for log n steps. That makes an overall complexity of n log n. This is definitely better than the n squared we got in bubble sort. In bubble sort, we had n times n, or n squared, as our efficiency. Log n is generally going to be less than n, but it's definitely never going to be greater than n. So we can say that the efficiency of merge sort is better than the efficiency of bubble sort. However, the space efficiency of merge sort is actually worse than bubble sort. In bubble sort, we were sorting in place, so we didn't need to use any extra arrays. Here, we frequently copied our values into new arrays. You can say that the auxiliary space, or the extra space we used, was linear. This complexity assumes that we got rid of arrays after we were done using them. At each step, we were copying values into new arrays, so we needed new arrays at some point. However, we could say that we were getting rid of the old ones whenever we were done. So we're not using a ton of new arrays every time. We really only need 2 different arrays at every step. The array that our numbers were in and the new array that we're copying the values into. In many cases, quicksort is one of the most efficient sorting algorithms. To do a quicksort, you essentially pick one of the values in the array at random, move all values larger than it above it, and all values below it lower than it. The value that you pick initially is called a pivot. You continue on recursively, picking a pivot in the upper and lower sections of the array, sorting them similarly until the whole array is sorted. Okay, let's watch this in action. First, we need to select a pivot. The convention is to pick the last element as your pivot, so let's go ahead and do that. Our first element is larger than our pivot, so we need to move it behind the pivot. However, we're doing an in-place sort, so we need to move the element in front of the pivot to make room. So in this step, we're moving 8 to the last block, 2 to the second to last block, and 10 all the way up to the first block. This seems a little counterintuitive. You would think that we would move 10 back and not forward. Just hold on for now, we'll see exactly why this works soon. So we did our shift, and now we can make another comparison. Now we get to take a look at 10. Since 10 is bigger than 2, we need to, again, move 10 back, move 2 up, and move whatever's in front of 2 up as well. Great, one more swap down. Finally, we have 0 at the front of our array, which is actually smaller than our pivot of 2. That's pretty great, but now we just move to the second element and do the same process with that one. Since 3 is greater than 2, we'll need to shift around everything again. Awesome, this is looking so much better. Since 7 is still bigger than 2, we need to do another comparison though. Here's the swap we need to make. And this is what our array looks like now. This is definitely good. 2 is in the right place, we've checked all the elements before it and we're sure they're less than it, and we've put all of these elements after it that are all definitely bigger than it. Because we're sure everything in the array below 2 is actually less than 2, and everything above 2 is greater than 2, we know that 2 is in the exact right place. I'm going to color code it so we know that we don't need to move it again. At this point, we normally do the same process for everything smaller than the pivot and everything bigger than the pivot. Let's start with the smaller part first. We select our pivot and compare to everything before. Since 0 is actually less than 1, there's nothing we need to do. And with just one comparison, we know that both of these are in the right place and we can move on. Now in the second half of the array, we select a pivot. Since 7 and 3 are both smaller than the pivot, we won't need to move them. However, 8 is bigger than the pivot, so we'll need to do a swap here. Now that our swap's complete, we can see that 8 and 10 are actually in their eventual positions. Everything less than 8 was already below 8, so we didn't need to move it at all. Okay, now we only have 2 elements left that maybe need to be sorted. Again, all we have to do here is assign 3 as a pivot and compare. We'll see that these 2 need to be switched, do that quickly, and then our whole array is done. As it turns out, the efficiency of quicksort is actually pretty complicated. First, let's just focus on the worst case. What would that look like? The magic of this algorithm is that it cuts the number of comparisons you need to do by splitting the array in half pretty much every time. So the worst case for us would be if we couldn't split the array in half and had to do all of the comparisons every time. You'll end up doing all of the comparisons if the pivots are actually already in the right place. Since 13 is already the biggest element, we'll end up comparing it to everything else on the first go and realizing that it doesn't need to move. This is a lot of comparisons to do at once, but the real problem happens when the next value is also the largest. Again, we end up comparing to everything smaller than it, and we're not saving any steps. Hopefully the number of comparisons here reminds you of bubble sort. Remember, in bubble sort, we would have to compare each element to the one next to it, again and again and again and again. Eventually we could leave off the ones that were at the end because we knew they were in the right place. The worst case of quicksort is exactly the same, which means that the worst case of quicksort is actually big O of n squared. For something called quicksort, that's a really terrible efficiency. However, quicksort is useful for two main reasons. First of all, the average and best case complexity are actually n log n. In a good case, the pivot will move down to the middle, and we'll get to divide the array in half every time. With our pivot in the middle, we can look at the other halves of the array and move their pivots to the middle too. Since these pivots are sorted, we know that everything else is sorted. So we're done really quickly. Here, because we're cutting the array in half every time, it'll end up looking a lot like merge sort. So again, that's why our efficiency is n log n. The average case is actually going to look a lot like this. We'll pick a random number, it'll move close to the middle, and so on and so on. However, if we know we're going to be getting arrays that are near sorted, we don't want to use quicksort, since that'll end up being the worst case every time. The second point is that you can do some optimizations with quicksort that'll make it run faster. For example, when you split your array, you can configure your program such that it runs both halves at the same time. It'll end up using the same amount of computing power, but it'll eat up less time. Also, rather than selecting the last element as a pivot, you could look at the last few elements and select the median of them as the pivot. Selecting the median will give you a better sense of what's in the middle of the array overall, so you have a better chance of moving your element in the middle and having that best case scenario. Also, this version of quicksort is in place, so we aren't using any extra space. Our space complexity is constant.